Aarushi Kulkarni, and this is my machine learning prediction project, which helps coaches and players tell the outcome of a pitch based on observed data in the baseball or softball context. Machine learning and the development of artificial intelligence continues to grow at a rapid pace with the age of technology and computer science jobs growing in demand. With this development, the use of predictive technology becomes more realistic to make systems more efficient. For example, in the medical field, a software may diagnose patients given an input of symptoms and previous health issues, which will be more effective than humans today. Sports are an area with vast possibilities of outcomes, meaning a lot of predictions built off of AI can be made in all sorts of sports. Humans don't have the analytical ability right now to examine every aspect of each player to predict the next situation in a sports game. For example, in baseball and softball, there are thousands of possible scenarios that can occur from a singular pitch. So, how can coaches and players in baseball or softball specifically tell the outcome of a pitch based on observed data? A simple machine learning predictive model using a technique called gradient descent takes features and examples as input in order to predict one of a couple possible outcomes for a pitch with its various features as a part of my project. Results show that upon running such programs numerous times with different iterations, the model actually grows stronger in accuracy. So, a little introduction. In a baseball or softball game, the people on defense do their best at each batter to adjust positioning based on what they think the outcome of the pitch will be. The machine learning model, in this case, predicts this event, which humans try to predict in real life, based on the pitch type, the release position, and the release speed of the pitch in a baseball scenario. An event that is the outcome will equate to either a strikeout, a strike, a ball, a hit, etc. On the screen, there's a list that shows the features based off of what the model takes. More background: if the pitch called to throw is a changeup or a slower pitch, the defense will move to the right if it is a right-handed batter and to the left otherwise, because there is a bigger chance that the batter will hit the slower pitch to that area. This is an example of humans predicting the outcome based off of a pitch and its data. However, humans and defenses in real games make mistakes which cost them the overall game. Coaches and team managers' goal is to maximize the amount of people getting out on the opposing team, and they can do so if they know the outcome of a certain pitch for a player by telling their pitcher to throw that particular pitch. Again, this is extremely difficult for a human to predict accurately, and personally, in my own experience, the defense and coaches almost never predict the event that will follow a pitch correctly. This is why my project is necessary. The project is split into two parts for numerical data The project is split into two parts for numerical data as input. One is a linear regression machine learning model implemented by Scratch, and the other uses a built-in Python machine learning library, which internally handles the linear regression implemented in the other code. Both implementations split the original dataset into 80% training and 20% testing data. They use training data to train on and the testing data to test the trained model. The dataset includes statistical numerical data about the at-bats of one specific player, where one example includes a list of features and characteristics regarding the pitch. The dataset is shown on the screen. On the right, the outcome of the pitch is in the description, and the image on the left shows all the possible outcomes for this specific implementation. There are 11 classes for the multi-class classification, meaning 11 possible outcomes, like I said, shown on the right. These are the outcomes that can be predicted based off of a pitch, which are used as ground truth values. The columns represent the different features of a pitch, excluding the description column, which are the outcomes, which store the possible output values, referred to as classes. The rows represent examples of each individual pitch, their attributes, and the outcome for the specific player as pictured in the dataset on the right. Outcomes to a pitch refer to the action done by the player as a result of the specific features of the said pitch. The prediction model written from scratch in one implementation uses multi-class classification as the basis of the machine learning model. The body of the model uses a gradient descent algorithm and a hypothesis function for the predicted outputs and calculating loss, which is the difference between the ground truth value and the predicted value. To get a predicted outcome, the hypothesis function takes a matrix of examples by features, which means there are examples on the rows of the features. On the rows of the matrix and features are the columns, which represents the input values, and another matrix of features by classes to represent the weights of each feature for each class of input. The body of the function uses a logistic regression equation called the sigmoid function to predict an output, and this is shown as implemented in the code on the screen. Theta refers to the weight, and X is the input feature. Since the inputs are matrices, they are multiplied through dot product, and the predicted class becomes a matrix of examples by classes. If the hypothesis is more than 0.5 for each input feature, the prediction is marked as correct. And this way, the algorithm builds a relationship with the input and output. To compare predicted outputs to the ground truth values, another matrix is created outside of the function, which has examples as the rows and the classes on the columns, and is filled on the basis that one example can only have one ground truth value. If that specific pitch has the outcome, the intersection of those corresponding indices gets marked with a 1. An example of this matrix is shown on the screen. With this process, the outcome matrix is built, and to use the prediction function, the ground truth values for the actual linear regression, the model uses gradient descent, implemented in a different function. This gradient descent function takes the inputs of the weight matrix and the ground truth matrix. It takes a learning rate, which in my case, I used 0.0005, takes the number of iterations for the gradient descent, which is known as the epochs. The more epochs, the more times the gradient descent occurs, and it establishes a stronger relationship between input and output, which increases accuracy of the prediction. So essentially, the more epochs there are, the higher the accuracy. During the gradient descent, for each epoch per iteration, the weights of each feature get updated based off of an equation. This updating is shown on the screen in the first code snippet. The gradient value is given as the dot product of the input matrix transposed and the loss matrix, which is calculated by subtracting the predicted output from the ground truth value for each corresponding indice of the respective matrices. And then this product is divided by the length of the matrix, which is the number of example inputs. The weights update equation is shown on the screen, and it is the learning rate multiplied by the gradient from the current weight value for each index in the weights matrix. Here, alpha is the learning rate as mentioned, X is the input features, which is transposed, H minus Y is the loss, and M is the learning rate. Doing so, each value for the weights of the features of the pitch that is currently being looked at is updated, and the function returns the matrix of the weights with the updated values after the process has occurred for the number of epochs. There are many results, and the quantities in the actual gradient descent and in the resulting updated weights that can be analyzed mathematically and graphically, the two shown to be calculated. The two analyses that have been done are the cost of the gradient descent and the accuracy. Cost in this case is defined as the error of the model, or how far the predicted output was from the truth, which is very similar to loss. The goal of the model is to essentially minimize the cost, which can be done by hypertuning parameters like learning rate and epochs of the gradient descent function. The cost function takes the input features matrix, the ground truth values, which is y, and the weights as input and calculates the model using the equations shown in the second code snippet. Generally, more epochs produces lower cost and higher accuracy, and seeing as the goal of the model is to minimize cost, more epochs is better. The accuracy of the model is calculated with a simple equation, which essentially looks at which predictions based off of the final weights are greater than 0.5. The other implementation of the same task utilizes the linear regression of a built-in Python machine learning library called scikit-learn, and which is referred to as sklearn in the code. The library's logistic regression function first sets the maximum number of iterations, or epochs in the other case, that the model should run for. The ground truth values, instead of using multi-class classification and denoting the output for a specific pitch with a 1, the values are stored in a list of the actual strings which represent the output from the description column of the dataset. The job of the gradient descent function in the other code in terms of training the model is done by the fit function of this library's logistic regression, which takes the input values with the ground truth as inputs and trains the model to establish a relationship between the two. The predict function internally processes the input using the same equation implemented in the hypothesis function from above. This entire process is shown in the code on the screen. The results analyzed from the first implementation are the accuracy of the model and the cost in order to find the number of epochs which maximize the accuracy while simultaneously minimizing the cost. Graphically, the accuracy is particularly low for this dataset because the dataset is very large with a lot of input values, which vary in range of magnitude and quantity. So hypertuning the parameters passed to the gradient descent function takes several runs and high computer power. The accuracy is graphed for each epoch, and which this run is for 10,000 epochs. The accuracy starts at 1 because the weights matrix is initialized to all 1s and eventually comes down as the model trains on the data. The accuracy comes down abruptly because for each epoch, the model makes a prediction, then updates the weights. The first half of the graph represents the accuracy of the training data, and the jump up in the middle is the start of the testing data. This is shown on one graph. The cost looks similar, graphically speaking, to the accuracy, and on the screen it is shown as the loss graph. It slopes down as the epochs increase because the model learns to minimize the loss by adjusting its weights for its different features based on the example it sees. At some point, the loss function starts to plateau, meaning that the model is done training. This indicates that the model is memorizing the data if the plateau starts to go back up, and this is bad because the loss is therefore getting not minimized. The ideal number of epochs is the minimum on the graph, and as we can see, it is approximately at 10,000 epochs by looking at the local minimum of the loss graph. So to maximize accuracy of the gradient descent, the value of epoch should be set around 10,000. However, since this is the maximum number of epochs used, it indicates that the loss could possibly go lower. For lower numbers of epochs, the graphs take the same shape with different values. So essentially, in order to use predictive technology to help coaches and players in a baseball game, scenario predict the outcome of a certain pitch, machine learning is used. A from-scratch implementation using the machine learning technique called gradient descent along with multi-class classification for a large data set has around 10% accuracy for initial parameters with no hypertuning of features or number of iterations. Similarly, using a built-in machine learning Python library has an accuracy with very little difference because of the lack of runs. The more time a model has to run on the same data in order to establish a relationship for the ideal number of epochs, the higher the accuracy will be. Thank you for listening.